Hello everyone, welcome to a new video from Ozen Engineering. Today I'll be speaking about digital twin real-time analysis. My name is Ahmed Ghandour. I'm an application engineer at Ozen Engineering. I have a bachelor mechanical engineering from Cairo University, Egypt, and master and PhD from University of Illinois, Chicago. I have over 10 years experience using finite elements, with majority of it with ANSYS products. I have experience with structural analysis, linear and nonlinear analysis, static and dynamic, thermal analysis. And in this presentation, I'll be presenting the work I did with contributions from my colleagues, Chris Kwon, Mesam Mehravran, Mohammed Sameh, Stephen Anchon Liu, and Vahid Miraftab. A little bit about our company. Ozen Engineering is an elite and is an ANSYS elite channel partner and distributor in California. Our work is focused entirely on simulation. We work with ANSYS Suite to help customers to develop products successfully. We provide software tools, and we also provide engineering consulting services using finite element analysis, computational fluid dynamics, electromagnetics, and other tools as well. In this video, I'll be talking about concepts of digital twin, and also will demonstrate digital twin prototypes we created at Ozen Engineering, including high frequency and low frequency models. I'm also gonna demonstrate digital twin IIOT, or Industrial Internet of Things deployment prototypes, also created at Ozen Engineering, including FLUENT application and Multiphysics application as well. So what is a digital twin? By definition, it's a connected virtual replica of an in-service physical asset. Basically, when we speak about replica, it's a virtual replica simulation. ANSYS technologies enable digital twin, 3D physics solvers, reduced order modeling, and twin builder platform. We use all these tools to create a replica of a physical model, which is usually in service. By connected, the concept is based on the ability to capture and handle big data enabled through Industrial Internet of Things, IIoT, featuring connected devices. It also enables system design and optimization, help with predictive maintenance, and optimize industrial asset management as well. So what are the key capabilities of simulation-based digital twin? As we can see, to do this, we need ANSYS simulation-based digital twin. This is the simulation model, and Industrial Internet of Things and data analytics tool for deployment. With this tool together, we can have ability to assist monitoring, asset monitoring. Basically, we need physical data acquisition, which may disrupt operation of an asset or fail in a harsh environment. Virtual sensors can replace physical sensors to enhance understanding of equipment. That's why having a virtual sensor can be very useful, which one of the advantages of having a digital twin. Predictive maintenance, it's another factor. Life experience data from an asset can be captured and used to predict real-time operating status through simulation-based learning. This can be done in the absence of historical data collection. Another thing is perform what if before applying a solution. And this can help in, as I said, in predictive maintenance by knowing what might happen if we change some variables or some of the inputs of the system. So what are the key benefits of simulation-based digital twin? Increase top-line revenue, manage bottom-line costs, gain and retain competitive edge. Digital twin is an interesting new technology, but the key benefits are financial, right? Digital twins offer value through both cost savings and new revenue. The rate of interest, or ROI, comes from 1, cost savings related to warranty and operation, 2, new revenue resulting from innovative business model and new products. So when should digital twin technology be applied? Mainly if we have expensive to replace or expensive if it fails unexpectedly. Second, when failure modes cannot be reliable, predicted with historical or IoT only data. So twin builder architecture and workflow. Typical workflow of twin builder is as follows. We create the simulation using and then using one of ANSYS products, and then we validate the physics to make sure that the physics is working fine, and then using ANSYS twin builder we will create the model, and then we create what's called ROM or reduced order model. Using twin builders, there's different ROMs, LTI, static ROM, dynamic ROM. All of these data will be used, and then we can use this to couple it with one of the digital twin partners for the deployment, either PTC or Rockwell or Microsoft, etc. So what is reduced order model or ROM that I mentioned in the previous slide? Basically, it's a simplified and condensed high-fidelity model. Support full range of ANSYS physics, reduce solve time by multiple orders of magnitude, similar to response surface methodology. This enables real-time savings. It offers ability to expand usage of 3D simulation model to users who work at the system level. And as you can see here on the right, this is a product. This is an output of a FLUENT CFD simulation after solving for 3 hours on 12 cores. But if we have the ROM of this model, we can get simulation real time. Okay. So what are the key capabilities of ANSYS Twin Builder? Twin Builder is a tool to use to generate digital twin, and it offers capabilities broadly grouped into 3 stages. First one is build, second one is validate, third one is deploy. So in build, basically includes system modeling, includes 0D application, 1D tools, and 3D ROMs. That's how you create your model using Twin Builder. Okay, and then once you have the model, you start validating based on design of experiment, optimization, prototype HMI, which is human-machine interface, graphics panels. Okay, then once we have the model and then we validate it, we start to deploy it using the IIOT, Industrial Internet of Things platforms, such as PTC or others. A lot of people usually ask, so what application I can use for digital twin, or what physics, what industry? With digital twin and twin builders, you can use it for actually variety of applications. You can see you can do it for battery or electrification, structural analysis, industrial automation, rotating machinery, heat exchangers, electric motors, and machines. All of this physics we can use. You can create a digital twin and use Twin Builder to create this twin model and help us in the predictive maintenance and understanding the system in better way and get results for that doesn't have sensor available for it, or it's hard to measure it in real life. So now we know what digital twin is and what is Twin Builder. So let's demonstrate some of the digital twin prototypes that we created at Ozen Engineering. The first one is high frequency 5G antenna phased array beamforming. This model was created by my colleague Mohammed Sameh. So as you can see here, the main physics here is a 5G antenna. Technology enables spatial multi-axis. Basically, we have an antenna that produce arrays, and we have a moving object, and then based on this arrays and the object, we can always trace where is this model, where exactly it is in an XY Z location based on this antenna. So what happened is he created a model using HFSS simulation. He created the ROM for that, for the antenna array, and then went to digital twin, and then we can see this is the output of the simulation. based on the finite element simulation, and then start to deploy it and compare real life data, the output of the simulation to the and the real location of the car. This is a physical model he created. You can see this is the target, laptop to monitor, and then location sensors and listeners to represent the antenna. Here in this video here, you can see a demo of what's happening. Here's a car moving in this space ground. You can see on the right and the left, we have the antennas that define the location of the car. And at the real time, we can see the location of the car in the domain predefined. Another representation here, you can see the car moving closer to one of the antennas, moving far from the antenna, based on how the car moved in this domain that we saw at the beginning. Okay, another demo. It's a low frequency electromagnetic field that's created by my colleagues Stephen Liu and Daniel Ismaili. Basically, we have a coil that will provide a DC current through this coil and get a magnetic field aligned with the axis of the coil. Here's the coil. This is a simulation created using Maxwell. And then based on ANSYS Maxwell, we create a ROM that will be used to provide the current and then extract the magnetic field of the coil, and then we measure it using a sensor for validation. So we create the model, create the ROM, and then validate it based on a magnetic field sensor. What we see here is the inside twin builder. We need to create the ROM, provide the input parameter, and then extract the output parameter that will be coming from the ROM, and then we compare that with the sensors that measure the real life magnetic field. To do this, the current is provided using a power supply, and we have a Python code that import live data from the power supply to be used as an input to the ROM inside the twin builder. Here's an example: the current changing and the power and the magnetic field changing with live data coming from the power supply based on the Python code, and we see the change in the magnetic field live happening. I don't have a video for that, but this what happened is that the field will change live, and we if we have the sensor in front of us, we can see a really good agreement between both of them. Okay, here's the workflow. The power supply provides the current to the system. This is the physical system, and then to the data collector, and then using the Python code, we provide it to the digital twin, and then we can see the results coming from the sensor and coming from the ROM, which have a really good agreement in reality. Okay, so now we'll show other prototypes that created at Ozen Engineering that demonstrate digital twin IIOT deployment. The first one, I created this one with my colleague Stephen Liu. This is one of our first digital twin prototypes. When we started to work on that, we decided to have something familiar to the area. So nothing is more famous than the Golden Gate Bridge. So for that, we created a CFD, computational fluid dynamics model, using ANSYS FLUENT. And then we can see here, this is some figures from the model. We created the model on FLUENT, and then we created the ROM inside ANSYS Workbench. And then to read the live data, we have Python code that read the live data of the air coming through the bridge. Basically, the main physics we are trying to do here is to predict the pressure on the walls of the bridge when there is wind coming in different directions. So based on the variation on the wind direction and velocity, what will be the change in the pressure on the bridge surfaces. Okay. What we see here is the fluid information about the fluid model. We use the polyhex core elements with 4.8 million elements and 14.5 million nodes. We also use the polyhex core mesh, it's a newest mesh technology inside FLUENT. And we use an ACT to get the topology of the area to get this mountain shapes based on topology ACT on ANSYS XStore. And we use turbulent model K epsilon realizable for our FLUENT model. This is some of the results. We have here the air velocity streamlines. Here the velocity streamlines and the pressure on the bridge. This only show the pressure on the bridge. This is focused streamline on the towers. We call this internal towers. And then we have the pressure on the mountain as well as the pressure on the bridge. So after we created the FLUENT model, we need to create the ROM. So inside FLUENT, we have to activate the FLUENT ROM feature. And then inside Workbench, we use a 3D ROM from Design Explorer to create the ROM based on the input, which in our case is the velocity in X direction and velocity in Y direction. We use a design of experiment to create this response surface. And we have an array of the points of interest, which we'll use then to create the ROM. So now we have the model, we have created the ROM, we need to read the data of the wind. So because we need the real live data, there is a website that provides the weather for the San Francisco airport. So using a Python code, we read this data, which give us a history for the last 2 hours, and then it's update the data live every 5 minutes. So that's what we take to our model. Live data every 5 minutes represent the wind direction and velocity. Once we run the model on the twin builder, we will see an automatic window will open up, which called ROM Viewer, which help us to visualize the results on different components and different time, which is very useful tool so we can see what's happening real life based on the time and the parts based on the data provided from the website. Okay, what we see here is a quick demo. Let me go over it very quickly. So basically, this is inside Twin Builder. We have the ROM. This is the ROM here, provided the X component and the Y component. And on the left, this is a data connector that read the data from the website, live data. And then what we see here is this is the output and this is the input. So to start, we need to initialize the model and then the model will start to initialize. When the model is initialized, we then have, we will see that it will open the ROM Viewer. At the same, here is the ROM Viewer is open. At the same time, we open a Python code that will read the data live about the San Francisco airport and then provide it to our ROM to get the result. Here's what's happening. We can see that the input, this is the velocity X and Y coming from online data. And at the same time, we'll see that the pressure on the bridge component are updated as well live where the data is changing. You can see the change, but it will be every few seconds because the data is coming every 5 minutes. One thing to mention, this Golden Gate Bridge project was selected by ANSYS to be to create a blog on that, and it was posted on ANSYS blog page, how to create a digital twin, where we have more detailed information about this model. So if you are interested, you can go to this website and read more about the Golden Gate Bridge digital twin model. Okay, another prototype, it's Multiphysics spiral coil. I created this model. Basically, we have a spiral model that have bimetallic materials, basically two metals with different thermal expansion coefficient, which means that when we heat it, it starts to deform in a different way. So if it's a straight line, it will bend. If it's a spiral, it will you fix one side, the other one will start rotating. So the objective of this model was to have a multiphysics model that basically will provide a current, so it will create a Joule heating. And when Joule heating is provided, so we have change in temperature, and then it will start deforming, so we'll have an angle deformation. So this is our input and output. And then we created a ROM for that, a dynamic ROM, because this is a transient analysis we performed using ANSYS mechanical. And then we validated the model and based on the data coming from the power supply, and then reading the data from a thermocouple to validate that the data coming from the physical model matching the data coming from the finite element model. And then we use the ROM to deploy this data using the internet, industrial internet of things. So what we see, this is a physical system. Here is a spiral connected to a power supply that provides a current. Once this is connected, the model will start to heat. This is thermocouple, we read the temperature. And then we have this hand here to measure the angle rotation, and the voltage will be shown here as well. So this is our input and output. What we see here is the model as a ROM, and then the data is coming, the current is provided based on taking from the power supply live, and then using a PTC ThingWorks platform, we can deploy this online, so we can see the results online. When we change the data here in the physical model, we can see online the change in the results based on the ROM of the model. So let me show you here a quick video on the model. So here is the power supply. It's provide the thermocouple. This is the physical model. This is the bimetallic spiral. So now, and this is the twin builder. Here's the ROM, and here is there is different output and the input. So once we initialize the twin model, so things start to work. So run our Python code that will read the current coming from the power supply, and then you can see the change in the voltage. Temperature is increasing, and the hand is rotating, which is the physical model. Now, if you go to the twin model, we will see the results here are matching what's happening live. So the results are changing live in front of us and also changing here on the system. So this is the digital twin of the system. Now, once we created that, we want to deploy that so people can see that anywhere and monitor the change. To do that, we are using the BTC ThingWorks platform, and we are using what's called Mashup for visualization. So now let me show you quickly after we deployed that and having the last phase of that, after reading the data from the power supply actually directly to the PTC platform without the need for any Python code. So here, this is the platform. Okay, that's where we created our model, uploaded our model. So first we activate the agent to activate the model on the PTC ThingWorks. Then we can see here, this is the platform. We can see the data here. Sorry, we can see this is a current coming from the power supply, and here is a change in the angle, change in the temperature, and change in the voltage. So we can see now the current is constant, voltage is constant, but the temperature and angle is changing, which happen in real life. And then if we change the current from 5.1 to 5.4, we can see change in the voltage because they are related. And then we can see the temperature start to keep increasing and the angle keep decreasing in the negative direction, which is reading the matching the live data coming from the thermocouple and the power supply and protractor. So this was one of our successful prototype that we had a complete deployment based on the digital twin and twin builder and IIOT using PTC ThingWorks. Okay, the last model we have today, which is also was deployed using PTC ThingWorks, was wind tunnel lift created by our colleague Mason Merivada. And basically, we have an airfoil that's and a wind facing it, like we can see here in this wind tunnel. So we provide a wind coming through the wind tunnel, meet the airfoil, which causes a lift force on the airfoil. So this is what we're trying to model and what we try to deploy as well. So basically, here's a system. We have a power supply. The power supply provides a voltage to the fan. When we change the voltage, the fan performance will increase or decrease, and consequently, the lift force will increase as well or decrease. This is the physical model. For the twin model, we have a twin builder created using a ROM or FMU created in FLUENT, which provide us with a lift force as well. And we have them in comparison to see how the model performs. So here's the model basically. And then we can see that once we have the model, we need to deploy this in IIOT. That could be done using PTC ThingWorks, SAP PEI, or Rockwell platform. In this example, we are using PTC ThingWorks. This simple model here is for an airfoil, but this could be scaled up to work on an airplane, not just to have the lift force, but we can also have a lot of information based on different sensors and different analysis. We can see like the yaw angle, for example. We can see some information coming from radars inside this, or antennas, or any mechanical systems. All of this, once we have a finite element for this, we can create the ROM. We can then deploy it online as well. So the deployment here, you can see we are showing an example of this digital twin deployed and functional on the cloud. So this one was deployed on the cloud. Basically, you can see here's the input, here's the output. This is based on a ROM that created based on FLUENT model, which have high fidelity prediction of this model. One thing to mention is the Mashup generated. Mashup is basically for visualization. This serves as a human-machine interface for this model. Here's what I mean by Mashup. You can see once we provide the voltage that's coming from the power supply automatically, we can see the lift force changing that's coming from, oh, sorry for that. That's coming from the ROM, and at the same time, we have the measurement on the physical model that have really good agreement for both of them. So to summarize this model, we have a finite element model created on FLUENT tools in ANSYS CFD analysis, and then we have created the ROM, and then we deploy this using PTC. We can see here the power supply reading coming directly to the physical model or to the deployed model, and then based on the ROM, we get the lift force that we can easily compare with the live data. That was the last case I have to present today. So if you have any question, feel free to contact us at info@ozeninc or call us on this number, or check ozeninc.com for more information about our company and our projects, especially for digital twin. Thank you so much, and I hope this video was helpful and that you learned something new. Thank you so much.